Good evening, students. So, in our previous class, as a part of atomic structure, we were enjoying the postulates of Niels Bohr's model, and we could also explain how spectral lines are formed. And with the help of Niels Bohr's model, we could derive an expression, alphanumerical expression for radius, and with a numerical conclusion also we made 0.53 n square by z. We also derived an expression for energy of electron. Instead of displaying, let me just work out on the board so that you also get used to this, how to work out energy values and what are the physical meanings we can derive out of the expression. That will dedicate this class for such conclusions, and we will try to calculate some energies also if possible. So, Niels Bohr's orbit's energy we derived, just let us recollect within 5 minutes once. So, this is nucleus, first orbit, second orbit, like that, and we have derived potential energy to be minus ZE square by R, kinetic energy to be ZE square by 2R, and total energy to be minus ZE square by 2R, and we also had an relation between them. Potential energy is given by twice the total energy, kinetic energy is minus of total energy. They change the sign of total energy, you will get kinetic energy. This will be a negative value, this will be a negative value, this will be a positive value. And for energy, what is the numerical expression and total alpha numerical expression? Energy total, we have got it, we substituted even R. So, minus 2 pi square m z square e power 4 by n square h square. So, this extent we have done. How did I get this expression? Simply I substituted the R expression. We have already derived R. So, n square h square by 4 pi square mz e square, that I substituted and I got this. And here what are the constant values? 2 is a constant, pi is a constant, m is a constant, electron charge is a constant, h is a constant. So, substituting all these constant values, we will get a numerical expression for total energy. It is given by minus 13.6 z square by n square electron volts per atom. This is where we stopped at the earlier class. So, this expression has got z square in the numerator, n square in the denominator. My dear students, be careful to how any expression is dependent on z and n in an atom, you should be careful. So, radius is n square by z, 0.53 n square by z. Energy minus 13.6 z square by n square. N is orbit number, z is atomic number of the single electron species, 1 for hydrogen, 2 for helium plus, 3 for lithium plus 2, like that. So, let us first try to understand the physical meaning of this expression, and we will try to work out some other interesting aspects. Energy is equal to minus 13.6 z square by n square electron volt per atom. There is a minus. So, what should you understand from this minus? Why there is a minus in energy expression of electron? Suppose you take an electron here, first orbit, second orbit, third orbit, like that infinite orbit. In the what do you mean by infinite orbit? An orbit, actually that is meaningless, it is a free electron. You can say that particular electron has nothing to do with this nucleus. So, with reference to this nucleus, that electron has neither kinetic energy nor potential energy nor total energy, all are zeros. And once electron enters into the vicinity of the atom, means influence of the nucleus, it will start getting attracted by the nucleus and it starts losing energy. Once it is here, it is now in the influence of the nucleus. So, this is an attracted electron, this is a free electron. Once electron is in attraction, it might have done some work while coming into this attraction. So, it has lost energy, and that energy lost from zero energy gives it negative value. So, as the electron comes down and down and down, its energy becomes more negative, because the attraction with the nucleus will increase. Attraction leads to drop in energy. So, electron has lost energy step by step while coming close to the nucleus. So, what I would like to advise the students to appreciate, electron closest to the nucleus will have least energy, because it has lost too much of energy to be attracted by the nucleus till first orbit. And if you calculate these energies E1, E2, E3, E infinity, let us enjoy some values. Suppose E1, the first orbit of hydrogen, what will be the energy of electron? Minus 13.6 into hydrogen, means Z square is 1 by 1. So, minus 13.6 electron volts. E2, in the second orbit, minus 13.6 by 2 square, means by 4, minus 3.4 electron volts. Third orbit, minus 13.6 by 3 square, minus 1.51 electron volts. E4, minus 13.6 by 4 square, minus 0.85 electron volts. So, what did you observe? This orbit's energy minus 13.6, here the energy is minus 3.4, here the energy is minus 1.51, here the energy is 0. And fourth orbit also, if you take, minus 0.85. What are these values? Most minus, less minus, still less minus, still less minus. As it is becoming less and less minus, means what? Its energy is increasing. So, the least energy is possessed by electron in the first orbit. The first orbit electron will have least energy in any hydrogen like species. So, let us now schematically draw all this again. So, you have got the least energy minus 13.6 electron volts per atom, minus 13.6, this is a minus, and second orbit energy minus 3.4 electron volts. Third is minus 1.81, sorry 1.51. Fourth one minus 0.85, infinite 0, 1, 2, 3, 4, infinity. What conclusions can we make? Very interesting. As you are going up, as you are going away from the nucleus, energy of electron is increasing, obvious. If it is totally knocked out from the atom, its energy becomes 0. That is also done. The more interesting feature is energy gap between the orbits. See, what is the difference between these two values? I am speaking about E2 minus E1, E2, E1, E3, E4, E infinity. See, between E2 and E3, E1 and E2, what is the energy difference? Minus 3.4 minus 13.6. Minus 3.4 high energy minus low energy. This becomes positive and you are going to get 10.2 electron volts. 10.2 electron volts is the energy difference between these two. But is it the same energy difference between second and third? 1.51 minus 3.4, approximately 1.9. Is it the same energy difference between those two? 1.51 and 0.85, somewhere around 0.65. So, what is the conclusion? See, energy gap between two successive orbits is gradually decreasing as you are moving away from the nucleus. So, it is not the energy gap is uniform. Definitely 2 to 1 is different from 3 to 2, 3 to 2 is lesser than 4 to 3. So, like that. So, the other conclusion is what? Energy gap between two orbits decreases. I think most of you must remember the physical gap between orbits is increasing. In radius we have done 1:3:5:7 is the physical gap between the orbits, successive orbits. Physical gap between the successive orbits is increasing. Energy gap between the two successive orbits is decreasing. You observe it 10.2, 1.9, 0.65 like. So, let us see something else. So, what is the conclusion? E1 minus E2 is much larger than E3 minus E2, much larger than E4 minus E3. Keeps on going like that. So, suppose someone says 2 to 1, 3 to 2, in which energy, which transition more energy is released. So, do not think it is also 2 to 1, this is also 3 to 2. In both cases the gap between the principal quantum numbers is only 1, therefore, energy will be same. That is a wrong conclusion. 2 to 1 will release a better photon, h nu 1, h nu 2, h nu 1 is greater than h nu 2. It is as simple as this. So, such a beautiful concept. So, let us work out something else. There is a beautiful conclusion what we can do. See, suppose this is the nucleus, this is the first orbit of Bohr's model, second orbit. So, what is the energy here? Minus 13.6. What is the energy here? Minus 3.4. In the infinite orbit, what is the energy? This is first orbit, second orbit. Infinite orbit, the energy is 0. Suppose electron is jumping from infinite orbit to first orbit. How much energy is lost? Infinite to first orbit electron jumped. A free electron has directly come and fallen in the first orbit of Bohr's hydrogen atom. How much energy is lost? 0 minus of minus 13.6. 13.6 electron volts energy is lost. Whereas, from infinite to second orbit, how much energy is lost? 0 minus 3.4. 3.4 electron volts is lost. Now, second to first, how much energy is lost? Minus 3.4 minus 13.6, 10.2 electron volts. Did you observe something? When electron is jumping from infinite to second, how how much energy is lost? Just 3.4. Just second to first, how much energy is lost? 10.2. So, infinite to second orbit gap is just 3.4, second to first is 10.2 gap. So, that is the point to be observed. As you move away from the nucleus, the energy gaps are decreasing between the orbits, in Niels Bohr's orbits. So, my dear students, I advise you to go through these energies thoroughly. So, let us now work out how to calculate the energy of a photon emitted in a transition. Yeah, now we will see. Before going to that, one more conclusion we will make. And suppose this is the nucleus, this is the first orbit, this is second orbit, this is third orbit, so on and so forth. What is the total energy here? Minus 13.6 electron volts. Here minus 3.4 electron volts by 4, minus 1.51 electron volts. How did I get these values? Minus 13.6 by n square, by 1 square, by 2 square, by 3 square. Now, what will be the potential energy? Potential energy, just now I told you, it is twice that of total energy. So, minus 27.2, just twice potential energy, twice 6.8 minus 3.02 electron volts. What is kinetic energy? Just change the sign of this. So, 13.6, 3.4 electron volts and 1.51 electron volts. What did you observe? As you are moving away from the nucleus, the total energy is increasing. This is the least value, minus is there, be careful. Potential energy is increasing as the electron is less and less attracted. As you move away from the nucleus, potential energy is decreasing. What is happening to potential energy is increasing. What is happening to kinetic energy? In the first orbit 13.6, second orbit 3.4, third orbit 1.51, becomes null and void in the infinite orbit. So, once you are moving away from the nucleus, the kinetic energy will decrease. So, in hydrogen like species close to the nucleus, electron moves very rapid. So, close to the nucleus, what should I say, energy of the electron is minimum. As you are moving away from the nucleus, energy of the electron keeps on increasing, as potential energy keeps on increasing, kinetic energy keeps on decreasing once you are moving into outsider orbits from the center. Now, let us focus on a transition. Suppose electron is jumping from one orbit to other orbit. What would happen? It will emit a radiation, and in the form of what? As per Albert Einstein, it is emitted in the form of a photon. How to calculate energy of a photon? Let us work out. So, let us consider a transition. This is N1, this is N2, this is nucleus. Means what? What is happening? An electron is jumping from N2 energy state to N1 energy state, N2 state to N1 state. So, once electron takes a transit, the other day we have seen that this also animation, we have seen some diagram. So, it emits radiation. So, that radiation has how much energy? H nu. That H nu is given by energy of N2th orbit minus energy of N1 orbit. Energy of N2 orbit minus energy of N1 orbit. So, now what is happening? What is the energy of N2 orbit? As per the expression we had, minus 2 pi square m z square e power 4 by N2 square H square, that is the energy of electron in N2th orbit. What is the energy of electron in N1 orbit? Minus 2 pi square m z square e power 4 by N1 square H square. Now I want the energy of the transition, this minus this, what would I get? So H nu is equal to minus 2 pi square m z square e power 4 by N2 square H square minus 2 pi square m z square e power 4 by N1 square H square. Simply I substituted energy of second orbit minus energy of first orbit. So what can I take in common? I can take 2 pi square m e power 4 by H square common. So what would I get? So 2 pi square H nu is equal to 2 pi square m z square e power 4 by H square is constant into minus of minus plus 1 by N1 square minus 1 by N2 square. And what is this expression made for? Whenever electron is jumping from N2 to N1, that much energy is released. I am using CGS units. So now if I substitute all constants, here, all the constants, I am going to get 13.6 z square, into 1 by N1 square minus 1 by N2 square electron volts. Did you observe something? This is energy of a photon. That is energy of a photon. It is not energy of any orbit. Orbit's energy is always expressed in negative value. But this is energy of a photon released when electron is jumping from one state to other state. When electron is jumping from one higher state to lower state, you know that much energy is lost, and that energy is given by 13.6 z square. It depends on in which species the transition is taking place. Is the 2 to 1 transition happening in hydrogen or helium? It makes a difference. So because in all the cases Z is not same, so transition energy also will not be same. So this is what? Energy of the transition, the energy of a photon released during a transition between N2 and N1. For example, see, now I would like to go for this h nu is what? Energy of a photon, 13.6 into z square. Suppose electron is jumping from 2 to 1, I should take 1 by 1 square minus 1 by 2 square. 1 by 1 square minus 1 by 2 square. So I am going to get 13.6 z square into 1 minus 1 by 4, 3 by 4. So this gives me 10.2 z square electron volts. What do you understand from this small expression? 10.2 z square electron volts are released. 2 to 1 transition, 2 to 1. It is not enough if you simply say 2 to 1 transition. not enough to say 2 to 1 transition. It is also, the energy depends on in which species it is happening. 2 to 1 transition in hydrogen gives only 10.2 because Z is 1, but in 2 to 1 transition in helium plus, Z being 2, 2 square 4, 10.2 into 4. So, 40.8 electron volts energy is released. So, it is not just the transition you should know, you should also know in which species the transition is taking place. So, my dear students, you now know how to calculate energy of electron in an orbit, energy of a transition from one orbit to the other orbit. So, let me just make you aware, energy of electron in a orbit is given by minus 13.6 Z square by N square electron volts per atom. Be careful, this is energy of an orbit, there is minus. Now, I am speaking about energy of a transition, N2 to N1. This is not energy of any orbit, it is energy of a photon emitted when electron jumps from N2 to N1, that is given by 13.6 into Z square into 1 by N1 square minus 1 by N2 square electron volt per atom. So, a transition energy depends on which species the transition is taking place. So, that is the beauty of it. One more aspect, suppose the transition is happening into infinity, you are bringing the electron from infinity to first orbit. So, what would you get? So, energy infinity to N1, infinity to 1 I mean to say. So, 13.6 Z square into 1 by 1 square minus 1 by infinity square. 1 by infinite square is what? 0. So, I am going to get 13.6 Z square electron volts. How do you call this energy as? When electron is jumping from infinite to first means this much energy you have to supply to take out the electron from central ground state to infinity state, and you can call this as IP, ionization potential. What do you mean by ionization potential? Taking electron from first orbit to infinite orbit. So, when electron jumped from infinite orbit to first orbit, this much radiation is released, means what? If you supply this much radiation to the first orbit electron, it will be knocked out into infinite level, means it will be totally knocked out from the atom, from the ground state atom. So, 13.6 Z square is always the IP of that species. What is the ionization potential of hydrogen? Or we will separately write. Ionization potential of hydrogen 13.6 into 1 square electron volts, 13.6 electron volts. IP of helium plus, IP of helium plus, what is Z of helium? 2. So, 13.6 into 2 square electron volts. So, 13.6 into 4, so 54.4. My dear students, you should be very careful. This is IP of what? Helium plus, means helium has already lost one electron. From here, if you want to remove electron, you require 54.4 electron volts. And with reference to helium, how do you call this energy as? With reference to this helium, this energy is IP2, because this is IP1 and this is going to be IP2. IP2 of helium is 13.6 into 2 square. Similarly, IP of lithium plus 2 is what? 13.6 into 3 square, you will get some value. But with reference to lithium, it should be called as IP3, because you are removing the third electron. We can only calculate this because we have derived all the expressions for a single electron species. So, my dear students, so the conclusion is you can calculate the energy of an orbit with that minus 13.6 into z square by n square. You can calculate energy of a transition 13.6 into z square into n by 1 by n1 square minus 1 by n2 square. Now, h nu is equal to 2 pi square m e power 4 z square by h square into 1 by n1 square minus 1 by n2 square. This you have already done. We have already done, that is energy of a photon. I want to know wavelength of a photon, wavelength. So, what should I do? hc by lambda is nu is c by lambda is equal to 2 pi square m e power 4 z square by h square into 1 by n1 square minus 1 by n2 square. Now, just keep lambda here, take the other values there. 1 by lambda is equal to 2 pi square m e power 4 z square by hc comes here, h cube c into 1 by n1 square minus 1 by n2 square. And these are all constants. 2 is a constant, pi is a constant, m is a constant, e is a constant, h is a constant, c is a constant. If I substitute all these values, I would in CGS, I am going to get 1 by lambda is equal to, this is Rydberg constant into z square to 1 by n1 square minus 1 by n2 square. We have successfully derived RH. This value only we have already discussed, 109677 value. That value was randomly worked out with arbitrarily worked out with that equation, and that value was found to be true with the help of Niels Bohr's atomic model. That is a grand success of Niels Bohr model as per single electron species are concerned. And this value exactly matches with, you take a spectral line and work out the lambda, that exactly matches with that 109677 centimeter inverse, which was arbitrarily taken in that equation. So, that is a grand success of Niels Bohr's model, which could verify that RH value is correct. So, this expression gives you what? Wavelength of a spectral line, wavelength of a spectral line. Suppose there is a spectral line formed in hydrogen atom, you can calculate lambda. That lambda is due to which transition you must know, and you can calculate spectral lines of other spectra of helium plus lithium plus 2 kind of things also. So, that is the most beautiful aspect we got from Niels Bohr's model. So, let me conclude with certain things. Again and again I am telling, because you are all supposed to know this, energy of electron will have minus 2 pi square m z square e power 4 by n square h square is the expression in CGS units. Its value is nothing but minus 13.6 z square by n square electron volts per atom. This is energy of electron in an orbit. Energy of a transition we have just done, n2 to n1 is given by what? 2 pi square m e power 4 z square by h square into 1 by n1 square minus 1 by n2 square, which can be written as 13.6 z square into 1 by n1 square minus 1 by n2 square in electron volts. Whenever you want energy of transition, go for this expression. You want lambda of a transition, 1 by lambda is equal to RH into Z square into 1 by N1 square minus 1 by N2 square. RH into Z square 1 by N1 square minus 1 by N2 square. So, these three are almost the useful expressions for you to calculate total energy, potential energy, kinetic energy of an electron in any species, because Z square is there. Which orbit? N square is there. With this expression, you can calculate the energy of any spectral line, energy of a photon released in any transition, that is the energy. And this expression is useful to calculate the wavelength of any spectral line, wavelength of any spectral line. Electron is jumping from some orbit to some orbit, what is the wavelength? So, based on this we can calculate, of course, the wavelengths of different series of lines formed in hydrogen spectrum. That is yet another grand success of Niels Bohr's model. We will see all those things. So, these are the expressions. If you observe carefully, all energy expressions are Z square related, every energy expression, let it be transition expression, let it be absolute energy expression, let it be wavelength of a spectrum, these are all Z square related, be careful, N square in the denominator. You must know all these values to solve problems. Now, how to calculate the velocity of an electron? Velocity of an electron in an orbit. There is an orbit, there is velocity. How to work out the velocity? Where did you get that velocity expression as per Bohr's model? In Bohr's model we have got a postulate, mvr is equal to nh by 2 pi. mvr is equal to nh by 2 pi. See, do not be carried away by a feeling. If n increases, velocity increases, never have such feelings, because there is r also. In the r there is n square, so that n and n will get cancelled, n will come down. So, be careful, check all the variables. So, we want V now. So, V is equal to nh by 2 pi m r. And what is the expression for r? We have n square h square by 4 pi square mze square. So, nh by 2 pi m in place of n square h square by 4 pi square mze square. This we have already derived from Bohr's model in CGS. So, I can cancel out m and m, I can cancel out 2 pi and 4 pi 2 pi times. So, I can cancel n and h and n and h, this will go up. What did I get? 2 pi z e square by n h. What are left in this particular expression? You have got 2 pi, z is a variable, e is a constant, n is a variable, h is a constant. So, if you substitute all this, it will be directly proportional to z and inversely proportional to n. So, velocity of electron will be directly proportional to z and inversely proportional to n. That is what we have already discussed earlier. As n increases, velocity decreases, therefore kinetic energy decreases. As you move away from the nucleus, the kinetic energy of electron decreases. So, that is what we have concluded here. What do you mean? How many times the electron revolves around the nucleus in hydrogen atom per second? That is called frequency of revolution. Frequency of revolution. How many times an electron revolves around the nucleus? Of course, if you work out this value, you are going to get some 2.18, do not worry about this, 10 power 8 z by n centimeters per second, z by n centimeters per second, directly proportional to z, inversely proportional to n centimeters per second. Na? So, this you remember. How to get frequency? How many times electron is revolving around the nucleus per second? How to calculate? In one revolution, how much distance it is covering? 2 pi r. So, electron is covering 2 pi r distance per revolution. But in 1 second, how much distance it travels? V. So, in 1 second, how many 2 pi r's are there? So, that is called frequency. Frequency is equal to velocity by 2 pi r. Velocity by 2 pi r. Velocity is distance travelled by electron per second. 2 pi r is distance travelled by electron per revolution. So, how much would you get? This is going to be V. Velocity has got what? Z by n. Z by n. So, some constant into Z by n. Velocity constant, constant, constant. Some constant into Z by n by in 2 pi r. 2 pi r is what? 0.53 into n square by z. So, constant, 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 again a constant. So, you can say frequency is directly proportional to z goes up, n comes down, z square by n cube. So, frequency of electron is directly proportional to z square. Is it hydrogen or helium plus or lithium plus 2 like by n cube. Got it? So, that is the issue. Now, my dear students, what could be the time period? How much time it will take to cover one revolution? Time period. So, time period will be reverse of frequency. So, you can say time period is directly proportional to n cube by z square. So, all these relations you must remember. See, everything is related to what common feature? Z and n. The student must remember whether it is z square or n square or z or n. So, how many so far we have discussed depend on z and n? Let us see. On z and n, what are all the features we have so far discussed? Radius 0.53 n square by z angstroms. Radius of orbit depends on z and n. N square is numerator, z is in denominator. Student must also remember this, whether it is n square or z square, n or z, numerator or denominator. If there is any constant, that also is better. It will give some physical picture for you. Energy of orbit, yeah, minus 13.6, z square in numerator, n square in denominator, electron volts per atom. Potential energy, twice of this, minus 27.2, z square by n square, electron volts, units. Kinetic energy, how much? 13.6, just change the sign, n square, electron volts per atom, all per atom only. And velocity 2.16 or 18, 10 power 8 z by n, centimeters per second. And frequency of revolution directly proportional to z square, inversely proportional to n cube. Time of revolution directly proportional to n cube, inversely proportional to z square. So, these are all the things one must always keep in mind, my dear students. Along with this, the Tredberg expression, energy of a photon, energy of photon in a transition 13.6 Z square 1 by N1 square minus 1 by N2 square. Energy of photon, wavelength of photon 1 by lambda Rydberg constant into Z square into 1 by N1 square minus 1 by N2 square. If possible, please copy down, repeat lecture you listen and copy down every expression. Everything was asked once or twice or thrice, many times in all the previous examinations. Not only for exam sake, one must learn all this because they have done so much. Niels Bohr, you must learn all this. So much they worked. Everything depends on which orbit, what is the nuclear power. So my dear students, let us first try to calculate wavelength of a spectral line now, or anything, suppose kinetic energy of electron in third orbit of helium plus. Suppose someone asks like this, kinetic energy, what is the expression for kinetic energy? Is equal to 13.6 Z square by N square, electron volts. So 13.6 Z helium 2 square by N square, third orbit 3 square. So 13.6 into 4 by 9 electron volts. Anything you can calculate, kinetic energy, potential energy, wavelength of a spectral line, like wavelength of a spectral line. Suppose electron is jumping from 4 to 2 in helium plus. Electron is jumping from 4th orbit to 2nd orbit in helium plus. You want to calculate energy of a spectral line, wavelength of spectral line. So 1 by lambda is equal to RH value 109677 into, this is helium, so 2 square, helium atomic number 2 square into 1 by 2 square minus 1 by 4 square, 1 by 2 square minus 1 by 4 square. So this is going to give me RH into 4 into what is LCM here 16, and this is going to 4 minus 1 3. So this goes 4 times. So RH into 3 by 4 is 1 by lambda. But what is lambda? So lambda is equal to 4 by 3 RH. And I already told you one thing, 1 by RH, don't waste your time calculating. 1 by 10967 centimeter inverse will become some centimeters, again convert into angstroms. You can always take 1 by RH as 912 angstroms. So this is equal to 4 by 3 into 912. This gives me 304. So 1216 angstroms. 1216 angstroms is the spectral line's wavelength when electron jumps from 4 to 2 in helium plus. Anything you can calculate, energy of a spectral line, wavelength of a spectral line, wave number of a spectral line, frequency of a spectral line using these expressions. Now this is a grand success of Niels Bohr's model to explain hydrogen spectrum. Let us see now. How to get hydrogen spectrum? Take hydrogen in discharge tube. Because I have taken H2 gas, don't think I have taken molecules. Because of the electric discharge they become atoms. So, you will have only H atoms. Even if you get 1 gram hydrogen, that will contain Avogadro number of hydrogen atoms in the sample. When I subject the gas to electric discharge, what will happen? The electrons will start getting excited into different energy states. Do not think same thing will happen in all the hydrogen atoms. Do not think same thing will happen in all the hydrogen atoms. In one hydrogen atom, electron may jump into second orbit, in one third, one it may go to fourth. Anything can happen, but in the excited state, electrons cannot stay for a long time. Fraction of a second they stay and they come back. While coming, they emit radiations, and those radiations are caught up on a spectrum. Analyzer, and you will have spectrum. You will have different series of lines that I already told you. Like this. That is how hydrogen spectrum looks. So, why so many series are formed? In each series, why so many lines are formed? Why the series are formed in different regions? This series is formed in ultraviolet region. This is formed in visible region. This is formed in infrared region. Why this is happening like this? There are 3 questions for you. Question 1, why so many lines? Question 2, why so many series? Why there is a gap between series? Question 3, why they are in different regions? To understand this, one must understand very clearly one thing. Energy is non-uniformly distributed, quantum physics, black body radiation. So, once you subject hydrogen atoms to electric discharge, do not think all hydrogen atoms will be excited to the same extent. They get excited to different states. If I throw chocolates into a classroom, all students will not receive same number of chocolates. One may receive some, one may receive 3, one may receive 5 like. Similarly, when hydrogen atoms are subjected to a random electric discharge with some potential, atoms get excited randomly, and there is no single hydrogen atom present in the discharge tube. You have got crores of hydrogen atoms. So, in different hydrogen atoms, electrons may get excited into different states. In one atom, electron may go here. In the other atom, electron may go here. In the other atom, electron may go still higher. So, at different hydrogen atoms, electron may get excited to different higher states. And while coming down, they emit radiations. While coming down to the ground state, they may come direct, they may come stepwise transitions. So, electron need not directly fall back. It may fall stepwise. It may fall here to give infrared some radiation. It may fall here some radiation. The next may be visible, some green. The next may be ultraviolet, which we can't see. Just for your sake, I am showing it like this. All transitions do not possess same frequency. All transitions do not possess same wavelength. All transitions do not give spectral lines in the same region. Why so many lines? Because so many hydrogen atoms. And for each transition there is a photon released, and transition need not be one per hydrogen atom. Within a single hydrogen atom there can be 5-6 transitions. Suppose electron is in the 6th principal energy level, it may come to 5th, then 4th, then 3rd, then 2nd, then 1st. 5 transitions may take place, and each transition will give a spectral line. So, it is very much convenient to understand that so many spectral lines, because so many hydrogen atoms, in each hydrogen atom there can be multiple transitions while falling back. So, each transition photon is emitted, so many transitions will emit so many photons, and all photons will go and put a spectral line each one. So, you will have so many spectral lines formed, and why difference in the regions, why some are ultraviolets, why some are visible light. Actually, we have already calculated certain interesting things. Suppose electron is jumping from second to first, electron is jumping from second to first. What is the energy of electron in the second state? 3.4 minus 3.4. What is the energy of electron in the first state? Minus 13.6. And what is the energy gap? 10.2 electron volts. So 10.2 electron volts is the energy of the photon obtained when electron jumps from 2 to 1. If electron jumps from infinity to 1, what is the energy gap? 0 minus 13.6. 13.6. So, infinity to 1 13.6 electron volts, 2 to 1 10.2 electron volts. So, whatever may be the transition that takes place into first orbit must have a maximum energy of 13.6 electron volts, a minimum of 10.2 electron volts. And the wavelengths corresponding to those photons, if you calculate, that happens to be in the ultraviolet light. Let us just work out that also in this class. Suppose electron is jumping from infinity to 1 and we know how to calculate wavelength. So, 1 by lambda is equal to Rydberg constant RH into hydrogen atom, Z is 1 into 1 by 1 square minus 1 by infinity square. 1 by infinity square is 0. So, RH, so lambda is equal to 1 by RH, 912 is the wavelength for this transition. Does it fall in visible region? What is the visible range? Somewhere around 3600 to 7800 angstroms. But you got a radiation with 912 angstroms below visible region, energy wise above visible region, ultraviolet. Had it been 2 to 1 transition, 1 by lambda is equal to RH into 1 by 1 square minus 1 by 2 square. This gives me RH into 3 by 4. And what is lambda? Lambda is equal to 4 by 3, 1 by RH. 1 by RH is 912. So, 4 by 3 into 912. So, this goes 304 times 1216 angstroms. So, this is the minimum wavelength, that is the maximum wavelength in that particular whenever electron jump into first orbit. So, that is all ultraviolet range. So, we get always spectrum in ultraviolet region. So, what is our next job? Let us go through hydrogen spectrum thoroughly and let us analyze series by series and try to get the wavelength range of every series, and that Lyman series, Balmer series, Paschen series, Fund series, whatever we have seen in hydrogen spectrum in the spectra discussion. Now, we will go in a qualitative manner to that particular aspect, then we will switch over to another fascinating model given by, and what are the drawbacks of Bohr's model we will discuss, and then we will go to switch the fascinating model de Broglie, who says electron is not a particle, he says electron is a wave. Again a new gate is opened, that we will see after finishing some problems on hydrogen spectrum, and we will also try to understand what are the drawbacks, why we are not confined to Bohr's model, everything. Till then, just go through all the expressions what I gave today, very important, just get them by heart, try to understand the physical meaning and try to calculate energy gaps between orbits randomly and be successful, my dear students. We will meet in our next class with hydrogen spectrum. Have a good day, enjoy, thank you.